Good afternoon, everyone. Thank you for having me, and thanks to Andrew for kind of setting the scene, very much with a hardware focus. And what I intend to kind of cover today is also addressing the software element, which hopefully kind of links back to some of the other talks we've had earlier about software-defined vehicles, differentiation, and the future of kind of automotive as well. So I'm Paolo Bargiacchi. I head up the automotive business unit at McLaren Applied. And I'll start by just kind of explaining who McLaren Applied are, because the first part of the name, quite famous, second half, definitely not. We were part of McLaren Group for the last kind of 30 years. We took technology that was developed in Formula One and kind of developed other products to send out to other industries, and that's kind of what we've been doing. But particularly within automotive, over the last 10 years, we've had a focus on power electronics and specifically the inverter development. So what you can see here is our kind of roadmap of development over the last 5 years. And the reason that I want to cover this is because collaboration has been a really important factor for a fundamental change in our strategy and our approach. So you can see in the kind of the top left hand, we started with our IPG1, Inverter Platform Generation 1, and this was kind of a bespoke product for a customer, McLaren, for the P1, world's first kind of hybrid hypercar. And we took that technology and brought it back into the motorsport realm with Formula E and Formula One. And you can see an iterative kind of series of processes where we were kind of one of the first people to debut silicon carbide for use in the inverter. But fundamentally, the important bit where the collaboration came in was this transition from IPG4 to IPG5, where we are today. Before, it was kind of very almost insular, looking at bespoke projects, whether it be for motorsport or individual automotive companies, and changing that to become far more of a product-driven strategy outwards to the market. And I want to cover two collaborative projects that we've been a part of, which have been fundamental to making that happen. So the first of which is the ESCAPE project, which was an APC-funded collaboration across 12 partners. It was about £20 million in size and was fundamentally aimed at addressing the entire kind of supply chain. So Will Drury this morning made reference to the value chain and the APC roadmap, and this was really kind of an ambitious project looking to address every element of that, right from kind of the epi layer growth all the way up to multiple kind of tier ones making products off the back of it. And it was having that safety net, so to speak, of co-developing alongside a series of partners, as well as, admittedly, some of the government funding support, that enabled that transition strategy to go to a kind of standard product that then can be sold out to the marketplace. There are a few kind of really tangible benefits of that project that came out as well, including acquisitions from Vishay into Newport Wafer Fab, which was to the tune of about £400 million total kind of investment. So really just underlines the success that those types of products can have. And the relationships that we formed with some of the partners in this project, we then carried on to another one, following the R&D, looking more at the manufacturing. So again, this was an Innovate UK project, but Drive an Electric Revolution instead of APC, and was working with kind of Microchip, but then Newcastle University and DER, about building automation into kind of the production line. So we've had two different ends of the spectrum there, the development of the value chain and the products, and then actually industrializing them as well. And that's been key from kind of collaboration. So that's our baseline and why we're here today. The core topic that I wanted to cover today, though, is really innovation that's happening in the power electronics space and how we can have both the kind of the hardware movements that Andrew's covered, but also we can marry that with software to kind of move forwards. And the way that we kind of describe the evolution in the automotive electrification landscape is via a series of waves. So these are the waves of electrification, and that is what you get when you unleash graduates with AI. Brilliant. So the first wave, really back in kind of 2008, Tesla pioneering innovation with the initial Roadster. We had the Leaf at the similar time, but fundamentally that was taking off-the-shelf technologies and shoehorning them into existing kind of architectures and products. Really, it took about 10 years for the OEMs to start to kind of catch up and bring EVs to market. Jaguar was one of the first of those in 2018 with the I-Pace, shortly followed by the EQC and the e-tron. But again, this was kind of fundamentally legacy technology, silicon IGBT-based power electronics, 400-volt kind of architectures. And where we are today is firmly within the third wave. And we're seeing this already, people migrating up to 800-volt architectures to enable the kind of ultra-fast charging as the EV charging rollout is still in its infancy, and people kind of have that range anxiety, a key barrier to entry. But then also the transition to silicon carbide and the domino of benefits that come with that. Andrew touched on them. When you kind of fundamentally improve your efficiency in the inverter and your conversion losses, you can downstream your cooling system, you can downsize your battery, and you can also go to a smaller, kind of lightweight, more sustainable electric motor. So it's the full kind of system optimization that it enables. But as well as just the hardware kind of foundations that silicon carbide enables, we want to look forward to the fourth wave and how we see that developing. And as electric vehicles continue to enter the marketplace, there's going to be an increased need for differentiation. Peter Wirth covered it this morning from Lotus's perspective, very much kind of focusing on the user interface and the software. But a big part of differentiation in the past for OEM brands has been the powertrain. And, you know, Gunny did say that, you know, we've got two really interesting vehicles here. The kind of concept Land Rover, the 5-litre supercharged V8, but that used to be a huge part of the buying purpose. You know, cars and particularly premium vehicles, luxury vehicles, they're not a commodity play. It's about what people kind of identify with. It's almost like an extension of their personalities. And for sure, the user interface and connectivity is going to be a massive factor going forwards. But we think that there's an element of powertrain that can still be kind of brought to the party. And arguably, where we are today, EVs are very kind of one-dimensional. So yes, incredible torque response, but you could kind of jump from one car to the next and not really notice a difference between the drivability. And this is where we think there's a kind of key opportunity for innovation. So we've already covered this. This is the first kind of hardware step, the 800-volt landscape. Just a quick proof point. Tesla are kind of the state of the art for the 400-volt system. Their 10 to 80% charge time is about half an hour. Hyundai and Kia have shown with their very first foray into the 800-volt space, you can get that down to 18 minutes straight away. So that's kind of 60% of the time. So that's a good proof point there. This then on the silicon carbide just highlights the circular kind of domino benefits, which I touched on earlier. That transition between silicon IGBTs and silicon carbide MOSFETs alone will net you about 7% either improvement in range, or we're seeing OEMs increasingly consider alternative options, so downsizing the battery by 7% to maintain range because it's the biggest, heaviest, most expensive, carbon-intensive component in the vehicle, or even looking at alternative chemistries like LFP batteries as well for the supply chain volatility. So that's very much the hardware side, and now let's get into kind of some of the software elements. So one of the things that we've kind of looked at implementing very much on the Wave 3 efficiency and system optimization point of view is multi-speed gate drivers. What you want effectively is a very fast gate driver speed for the majority of your running, the WLTP cycle, very efficient. But what that comes with is limitations, effectively in terms of kind of momentum. You risk overshoot, which then would cause kind of restrictions being put in place on the inverter performance. What we do is switch over to an alternative gate driver speed, which is slower at that kind of high performance end and gives you that headroom to maintain the breadth of performance without having to sacrifice efficiency. Following that up, we've also got the ability to change between modulation strategies in the control element of the motor as well. So fundamentally, we've got two different strategies here, space vector or discontinuous, and all you need to know is that one's more optimized at low speed, low power, and the other at high speed, high power, and we can seamlessly transition in between the two. And again, this is about broadening the kind of the performance window and seeing how we can marry the hardware and software to do exactly that. And my last one on the kind of the third wave, and it bridges this gap into the fourth wave now, is on variable switching frequency. So historically, kind of inverters have been pinned to one, maybe two pre-selected switching frequencies, which would fundamentally mean they would switch too fast when the motor is at low speed, or then restrict the top end speed of the motor performance as well. What we've developed is a kind of control strategy which in real time varies that switching frequency based on the motor kind of operating condition. So at low speed, we pull it all the way down. We maintain a kind of fixed ratio, so you always get the quality of the sine wave profile that gives the kind of appropriate motor control output, but then we can bring that all the way up to kind of 32 kilohertz, maximizing the potential of silicon carbide. And you can see just a couple of examples here of comparing your continuously variable option to a series of different fixed strategies over a WLTP cycle. It's worth 1 to 2 to 3%, which is massive in terms of what it then enables on the battery side or the range perspective. But continuously variable switching is also then what enables some of the more kind of interesting fourth wave type features that we can develop. So if we put kind of standard just performance and efficiency to one side, what can we then do to add kind of character back into the drivetrain? And there's a number of different things that we can do. This clearly is not an engineering graph, so the engineers in the room, please just, this is for my storytelling purposes. But fundamentally, this is what the motor wants to see, a perfect kind of sine wave of current. What the inverter effectively does is approximates that sine wave by switching in and out. And this is where a lot of the benefits of silicon carbide come from. You can switch more often so that you get a more granular view and approximation of that sine wave. But what this does mean is because it's imperfect, it produces a load of resonance within the motor, which effectively kind of creates a signal of noise. And that manifests itself in excess heat, loss of efficiency, but also genuine noise and vibration as well. So bringing that harshness into the powertrain, kind of annoying whine, which nobody wants. So we're looking at how we can use the motor control software to effectively embody the principles of active noise cancellation from headphones to actively mitigate this. So you've got loads of resonance points happening across the motor, but some of the major ones are on the third, fifth, and seventh order harmonics, and we can program that in to effectively inject a cancelled out version of that excitation profile, and then when the two sum to zero, you improve refinement of the vehicle. So this can be used in a number of different ways. For a brand like Range Rover or Rolls-Royce, you can very much play on the refinement aspect, cancelling noise out at the source. But what we think is also interesting, maybe for more like a Jaguar type brand, is how you can use those harmonics to inject into the motor and add audible character back into the powertrain at the source. So we've seen lots of kind of interim solutions where brands are recognizing that EV powertrains are a bit sterile, but that has started to go down the route of kind of artificial noises played through speakers, which we know a lot of customers that doesn't really resonate with them. So what we're looking at here is something a little bit more authentic. It's driven straight out of the kind of electric motor powertrain and would be tunable to each OEM's vision of their kind of brand characteristics. But it also gives us some kind of drivability controls as well. So whether that be looking at the DC ripple coming in from the battery and actively mitigating that to smooth out the torque response, or even modeling the engagement and disengagement of the teeth within the gears on the transmission as it zero crosses between forward and reverse, we can use these clever kind of modeling loops to improve the overall customer experience. Where this has taken us to, we're currently kind of implementing this into two of our products. The IPG5 is effectively the output of the ESCAPE program that I mentioned right at the start that was born out of collaboration. And on the right-hand side is effectively a product extension of that, which is IPG5X. It's about integrating then into electric motors and transmissions. And we see this increasingly being important in the future, not just with the motor and the transmission, but potentially other power electronics as well. So that is all I wanted to cover. Thank you for your time. And if anyone wants to talk to it more after, please, you'll find me outside. Thank you.